Okay, we have another problem for you using our combined gas law. Remember we mentioned it's good to do P1, V1, T1, P2, V2, and T2 is the best way to approach all of these problems. Just write that as a given list right off the bat, and as you begin to fill it, it will help you use the combined gas law better each time. So here we go. We're going to read our problem. This time we have a syringe, so we got a syringe for our problem here, and we said it's being pushed on by 1 atmosphere of pressure. So we set it, and it's at 60 milliliters. So we set our syringe to 60 milliliters, and the room atmosphere is pushing down on that right now. If it wasn't, my syringe would pop out. But it's pushing down, and it's holding it steady at 60 milliliters. Okay? And so we have our first volume number, so we're going to put it in our first volume situation, 60 milliliters. And we have our atmosphere, ATMs, that's a pressure. It's our first pressure mentioned in the problem. So we'll put that in the P1 area. And as we read on, it says, we add more pressure to the syringe, so we're going to add pressure to the back of the syringe, and we're going to seal it at the top here, and we're going to force the syringe to get smaller. To do that, I have to add more pressure to it. So the question is this: if I push the syringe down to 30 milliliters, that's another measurement of volume, so we're going to put that in the V2 spot. The question is, what is the new pressure? So I put a question mark there. And as you note that we're in the same room, we didn't change the temperature, so that means the temperature remains constant. So if the temperature remains constant, then it's not going to be used in our formula. So let's write our combined gas law. It is P1V1 over T1, which is P2V2 over T2. We have multiplication on the top. Okay? So we look at our equation. We notice that temperatures were not mentioned, so we're just going to remove them from our problem. We don't need to use them. So we get this new equation, P1 and V1 equals P2 times V2. So that's the new mathematical law we're going to use. That's Boyle's law. It was hidden inside of the combined gas law. And so our problem is, if I seal the system and I push extra hard on it to get it down to 30 milliliters, what's the pressure I'm pushing at, including the atmosphere around here? So I've got to add extra pressure. So our goal is to find that number. So we took our combined gas law, we removed the temperature symbols, and now we're just going to take our numbers here and plug them into the equation. But remember, back here, we can have any one of these units. We have atmospheres, so we're all set up. And it's no problem. That's what the atmosphere is pushing down right now, all the gas particles in the room. And so we're just going to solve for it. We can leave it in atmospheres, and so our answer will come out in atmospheres. So P1 was 1.0 atmosphere. V1, which is next to it, is 60 mLs. P2 is unknown, so I'm going to put an X in that place, so we don't got to solve for it. And then we have V2 is 30 milliliters. To get X by itself, since I'm multiplying by 30, we got to divide by 30. So we push this to the other side. We get divided by 30, which is our correct algebra. And now X is all by itself. And we simply got to do the math. So we take our calculator. We go 1 times 60, which is 60. Okay? And then we divide 60 by 30, which is just basically 2. And we see that the milliliters on top cancel out the milliliter name on the bottom. We get a final answer for X to be 2.0, and the ATM is not removed, so we have the atmosphere. So for me, to get this syringe to go down to 30 milliliters, once it's a sealed system, I have to push an extra atmosphere with the atmosphere around it, so I have 2 atmospheres pushing on the syringe to keep it at 30 milliliters. Okay? So that's how we did it. But before we go, let's check this to see if we're correct. Okay? In this problem, temperature remained constant. It did not change. So we put our finger at what remains constant. Okay? Then what we did is we made the volume smaller. To make the volume smaller means I have to increase the pressure on that system. And so I pushed harder, and so the pressure went from 1 atmosphere up to 2 atmospheres. So this predicts it should go up. We did get a larger answer, so it is in the correct range, okay? So that's how we do the combined gas law with pressure and volume. Okay, now for our last problem using the combined gas law. So this one we made a little bit more complex, but if you keep using the same practices we've given you, it's nothing more difficult, okay? So this is a combined gas law problem. We're going to write out our given list. So we're going to go P1, V1, T1, P2, V2, T2, and we're going to start reading our problem. Okay? And so we go along. It says that we have a 15-liter weather balloon is released from the ground at a temperature of 25 degrees Celsius and a pressure of 760 millimeters of mercury. High above the earth, the balloon expands because it goes up with less pressure, and the pressure drops to 550 millimeters of mercury. What is the temperature of that height? Now we know it's going to get colder as we go up in the atmosphere, so our goal is to find that final temperature. So we go back to our problem. 15 liters. Liters is a volume. So that's going to be our first liter number. Okay? We read along. We know our next number is 25 degrees Celsius. That's our first temperature number we've run across, so 25 degrees Celsius. Then it says, at a pressure of 760, it's our first pressure. 760, we're using millimeters of mercury this time in this problem. No problem. And we go on, and it says that the balloon expands to 19 liters. Well, that's our new volume, 19 liters, okay? And the pressure drops because we go higher up in the atmosphere. The balloon wants to expand because there's less pushing on it. 550 is our second pressure mentioned, so we'll put that in the second pressure position, our millimeters of mercury again. And then it says at that temperature, at that height, what is the temperature? So my question mark goes there, okay? So nothing fell out this time. So that means we're going to use every single one of our symbols in the math. And our Celsius was being used, and we need to convert that to kelvins. So 25 plus 293 is 298 Kelvin. So we're going to use Kelvin in our formula, okay? So let's put our numbers together and rearrange everything. I will put the math down here below the problem. We have, remember, it's P1 times V1 over T1 equals P2 times V2 over T2, okay? So let's plug our numbers into our equation. P1 goes on the top. So we have P1, which is 760 mmHgs. We have V1 next to it, so V1, 15 liters. On the bottom, we have our T1, which is kelvins, 298. And we have P2 on the other side of the equation. That's 550 millimeters of mercury. And then we have, next to that, our V2, which was 19 liters. And then we have our unknown T. We'll put an X there for a question mark. And so now we have a little bit more complex problem. So here's the problem we're running across. We got to get X by itself. A lot of students want to just push these two over to the other side and divide, but when we do that, we solve for 1 over X. And that's not what we're looking for. We're looking for X, but X on the top. And the way I like to do these, I think is much simpler, is anytime you have something that you want to solve for on the bottom, and it's on the bottom fractions like that, an unknown, I find it easier just to flip both sides, because as long as you do it to both sides, it works out mathematically correct. So we're going to take and flip both these equations over, and so it's real simple. You ready? I'm going to do it. I'm going to flip this one over first, so I get 298, okay, over 760 and 15. Now I'm going to make the numbers a little easier. I'll talk about the units in a little bit. Then I'm going to flip this side over. So X goes on top. I get then 550 on the bottom, and then 19. Okay? If we look at our units, we can see that the millimeters, and we bring the 550 over to this side. I'm dividing now, so to bring it over here, it becomes multiplication. Remember? Opposite. If you're dividing by something and you move to the other side, it becomes multiplication. So something that's multiplication becomes division. I'm dividing by 19. I'm going to move that to the other side. Squeeze that in there. 19. Now we have x by itself. And you can see back here we have millimeters of mercury on both sides. They will cancel out. We got liters on both sides. They will cancel out. Kelvins will be our leftover unit. So our answer will be in kelvins. So we're going to quickly do our math. And we take 550 times 19, push equals, times 298, push equals, then push divided by 760, pushing equals, and then divided by 15, pushing equals. I get an answer of 273.16 Kelvin. Okay? So that means that as this balloon rose up into the atmosphere, the temperature to keep these conditions and all stuff change end up going down to 273. If we look back here, to go from Kelvin back to Celsius, if I have plus 273, remember the opposite algebra, we put minus 273 to turn it back into Celsius. So what do you think 273 minus 273 is? 0 degrees. Okay, well it's just barely above it, it's like 0.16. So I could write this as 0.16 degrees Celsius if I wanted to convert it. Okay, so the temperature at that height was basically freezing temperature for water. So very cold up in the atmosphere. Okay, so that was a complex problem. We used every one of our formula variables. We had an unknown on the bottom, so we had to flip our equations over. We still had to do a little bit of rearranging algebra, and then we even at the end went back and found degrees Celsius by subtracting 273. So that is how you do a problem like that.